In this lecture, I will be reviewing moments of inertia. This is because we encounter them in rigid body dynamics in circular motion. The objectives for this lecture is to review the area moments of inertia, and only a definition will be provided since you have covered this comprehensively in statics. The second objective is to present the mass moment of inertia. You will cover a little bit more on this topic in theory of machines. I will only give a working definition of area moment of inertia. The moments of inertia of a plane area, say area A, about the axis, about x and y axis in its plane and about the z axis to the plane, are defined as Ix is the integral of y squared dA and Iy is the integral of x squared dA, while Iz is the integral of r squared dA. Note that r squared is equals to x squared plus y squared. You can see this from the figure. And Iz is equals to Ix plus Iy. And the units are in meters to the power 4 or millimeters to the power 4. These are some common area of moments that should be familiar to you. If you are in doubt of their derivation or how we arrive at these area moments, please go through your notes in statics to refresh your mind. Now we will review the mass moment of inertia, which is central to understanding rigid body dynamics or some aspect of rigid body dynamics. The equation of rotational motion about an axis normal to the plane of motion for a rigid body in plane motion contains an integral which depends on the distribution of mass with respect to the moment axis. This is usually encountered whenever a rigid body has an angular acceleration about its axis rotation. An understanding of mass moment of inertia is therefore necessary for the study of rigid bodies dynamics because we will encounter these integrals. Consider the body of mass m of this figure rotating about an axis OO with an angular acceleration alpha. Every particle in the body will move in parallel planes that are normal to the rotation axis OO. An element of mass dm will have a tangential acceleration at component along its circular path with magnitude r alpha. Now, using Newton's second law of motion, where we say F is equals to ma, the resultant tangential force F on this element will be r alpha, which is the acceleration, times dm, which is the mass. The moment of this force about the axis OO is r alpha dm times the perpendicular distance r, which gives r squared dm. Therefore, the sum of the moments of these forces for all elements will be the integral of r squared alpha dm. For rigid bodies, the angular acceleration will remain the same for all the elements. Hence, we can take it outside the integral and we will have alpha outside the integral of r squared dm. And the integral r squared dm is the mass moment of inertia. Therefore, I equals to integral r squared dm, which is equation 1, is our mass moment of inertia. Just as the mass m of a body is a measure of the resistance to translational acceleration, the moment of inertia I is a measure of resistance to rotational acceleration of the body. The moment of inertia integral can also be written as the summation of Ri square mi, where Ri is the radial distance from the inertia axis to the representative particle of mass mi, where the summation is taken over all the particles of the body. If the density of this body is rho and is constant throughout the body, the moment of inertia becomes I is equals to rho integral r squared dv, where dv is the element of the volume. In a case where the density is not uniform all through the body, and if it can be expressed as a function of the coordinates of the body, then it should be within the integral sign and should be integrated. Now we consider another property, the radius of gyration, k, of a mass, m, about an axis for which the moment of inertia is I, is defined as k equals the square root of I over m. Or we can then write that I is equals to k square m. Therefore, k is the measure of the distribution of mass m of a given body about the axis in question. If all the mass m of a body could be concentrated at a distance k from the axis, the moment of inertia would be unchanged. If in a problem you have the mass and the radius of gyration, you can easily compute the moment of inertia using equation 3. If we know the moment of inertia of a body about the mass center, we can easily compute for any parallel axis. This is called the parallel axis theorem. To show this, we will consider the figure with two parallel axes through the mass center G and through some other point, say C. R0 and R are the radial distances from G and C to any element of mass respectively, say the mass dm. Note that the distance between the parallel axes is d. From the cosine rule, we can find our r square equals to r0 square plus dm square plus 2r0 d cos theta. We now substitute this into the definition for the moment of inertia. And as we substitute this into the equation of moment of inertia, it gives us I is equals to the integral r squared dm. So you put in your r squared into the integral and you get this equation. The first integral is the moment of inertia about the mass center. The second term is md squared, and the third integral is equals to 0 because the u-coordinate of the mass center with respect to the axis through G is 0. Therefore, the parallel axis theorem is I is equals to the moment of inertia through the mass center plus md squared. Conditions for these to work are one of the axes must go through the mass center of the body, and B, the body axis must be parallel. When we now substitute the radii of gyration into equation 4, we get equation 5, which is the parallel axis theorem for obtaining the radius of gyration k about an axis that has a distance d from the axis through the mass center G. Note that for a three-dimensional motion, components of rotation may occur about more than one axis, and we use double subscripts to denote them as shown in equation 6. Please go through the sample problems on your own, and if you have any questions, kindly contact me. Thank you for listening. Bye-bye.